everybody, this is your video for lesson 31. We're going to talk about linear approximation, which is just a fancy way to talk about that we're going to use a tangent line and we're going to use it to approximate function values. So reviewing what we already know a little bit about tangent lines is that when we are writing a tangent line to a function, we are writing it at a particular point and we are identifying the slope at that point. So if the point we're using is x equals a, then I can write my point as a comma f of a, and I can represent my slope as f prime of a. Okay. Derivative of the original function tells you the slope of the tangent line. We identify an ordered pair to put the tangent line, and what we should see is, and what we're going to use the tangent line for is, because the tangent line and the function are so close to each other, they're identical. As you stay close to the point where the tangent line is, there's almost no difference between values of the function and values on the tangent line. The tangent line can approximate function values. If I want to know f of something very close to a, I could use L of that value, and the output would be very, very close to what the function would give me for the output. Okay. The way we build this tangent line, once we identify the point and the slope, y minus f of a equals f prime of a times x minus a. That's just a version of y minus y1 equals m times x minus x1. Okay. When we use the tangent line to approximate function values, we specifically call that linearization. And so to remind you again, what are we going to do? We're going to use tangent line equation and it's going to approximate function values. Okay. Now, we don't really have a good appreciation of how cool this is because we have the ability to do all kinds of approximation problems, or we can basically evaluate anything we want, that even things that are a little bit more difficult because we have a calculator. So, but I'm going to use this as an example. If we wanted to estimate values of the function 1 over x, I am going to, specifically if I wanted to evaluate 1 over 10.2, I am going to put a tangent line at x equals 10, because when I draw a tangent line to 1 over x at x equals 10, that tangent line is going to be, number one, easier to work with, and number two, going to give us a good approximations of 1 over things close to 10. Okay, I want to show you again what kind of the idea is here. Let me grab a little Desmos graph, move this guy out of the way, pull this over here. Okay. Let's do y equals 1 over x. Okay. And if I blow this up a little bit. Now we know, okay, we're kind of spoiled when we have a graph like this, because if I want to do 1 over any value, I can just scroll right along here and find all those individual values. But without a graph, without a tool to calculate, if we wanted to figure out what 1 over 10.2 was close to. Using the 1 over function might not be our best choice, but I can make a tangent line to the 1 over function, and the tangent line can act just like that function as long as I stay close to where I put the line. Okay. All right, so x equals 10, f of 10 would be 1 over 10 for this particular function. And so my line would start looking like this. In general, a linear function is always going to be easier to work with. Linearization works best or shows its power most when we use it on a really, really complicated function. I'm doing it on a pretty simple function for this example, so it's something we can work with. But if it's something like 1 over the square root of x, which might be a lot harder to estimate, a tangent line could be a great way to be able to estimate, and that's usually how these initial functions values were calculated. All right, so I need f prime of x. If f of x is 1 over x, or x to the negative 1, the f prime function would be negative 1x to the negative 2, or negative 1 over x squared. Remember, bless you, that's my son. You can always pause this and wind it back. So if I'm looking at f prime of 10, that's 1 over 100. Negative 1 over 100. So put that right here. Negative 1 over 100. I am going to graph that. Okay, so y minus 1/10 equals negative 1 over 100. So the red graph is the 1 over x graph, and the blue graph is our tangent line graph. And you can see, when we're somewhere not very close to the tangency point, these functions are very different. When x is 1, they don't give very similar values. When x is 2, their values are a little closer. If we let's adjust this a little bit. Let's go 0 to, let's go here, so we'll just kind of try to, okay, there we go. All right, so if we look at these two functions, you can see as we start getting closer and closer to where x equals 10, they start to become, well, literally, you can't distinguish them. If I space out a little bit more, whoops, there we go. Now you can see the space between them. But when you look at the scale, you see the actual difference between the two is a lot smaller. And the closer we get to x equals 10, the less of a difference there is. And now you can see they're almost indistinguishable again. I would have to zoom out a bunch. And you can sort of see, so you can see this is the power of linearization. When you do a tangent line, when you get close enough to where the tangent line point is, the two functions, you can barely tell the difference between the two, even though they are two different functions. So if I want to find 1 over 10.2, this tangent line with an x of 10.2 will give me a pretty close estimate. So let's put that 10.2 in here. Okay, since my tangent line is at 10, the tangent line should be a pretty good estimate of what happens at 10.2. Okay. This is negative 100 times 0.2. Now, if I finish doing my arithmetic, I'm going to kind of scroll down here and do some extra arithmetic spaces. So my y would be negative 1 over 100 times 2 over 10 plus 1 over 10. If I solve for y, so negative 2 over 1,000 plus 1 over 10, which I times that by 100, negative 2 over 1,000 plus 100 over 1,000 is 98 over 1,000, 0.098. So my tangent line's telling me that at 10.2, the tangent line value is 0.098. If I go to the function curve, I think we might find that those are actually really close, if not identical. I don't even know if we can see the difference. Okay. All right. Or if I can copy that. All right. So watch. I'm going to stick a 10.2 in this guy. It's going to take off the graph. But it... Oh, crap. Didn't do that the way I wanted to. Sugar muggers. Let's do this. Plus 1/10. Okay. And when I do 1 over 10.2, 1 over 10.2 is a little bit bigger than 0.098. 10.2 plugged into my tangent line gave me 0.098. So we're accurate to the 10, I would say 10 thousandths, almost 100 thousandths place because we consider that 0. Tangent line approximation, very, very, very good. As long as we're close to where we put the tangent line. If I wanted to use this same equation and do like, well, what's 1 over 11 versus what would this be? Whoops. Still good, but maybe not quite as good. Still pretty good. We're still pretty close to 10. What if I went to like, and these two actually get closer. Let's start far away. Let's go like 4. You dummy. 4 versus 4. Yeah, and you can see, okay, now those aren't as good. So it's the difference between, we don't actually have the graphs anymore, but if we went back to our graphs, we could see it's the difference between looking at what was happening between the two graphs, the space between them around 10, and the space between them at 4. Now, the cool thing is you can roll back and you can look at that and see that our estimate was a little bit smaller than the actual number. Whether the estimate is going to be bigger or smaller than the true value has to do with where the tangent line is going to be relative to the curve. If the tangent line is over the curve, because the curve is concave down, the tangent line you would draw would overestimate your values. If you've got a concave up curve and the tangent lines go under the curve, the tangent lines are going to underestimate. So the secret to whether your estimate is an over or under estimate is the concavity around tangency point. Okay. Now what we saw for this function is the actual value that we got with 1 over x with 10.2. 1 over 10.2 was 0.9803, blah, 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 blah. This answer was a little bit smaller. We're not always going to be able to look at the true value and to make a direct comparison, but the concavity can tell us if our tangent line number is actually smaller or bigger. So let's talk about 1 over x. Your first derivative was negative x to the negative 2, because 1 over x is x to the negative 1. Your second derivative is 2x to the negative 3. And at x equals 10, that becomes 2 over 10 cubed, which is greater than 0. So what that means is f is concave up around x equals 10. So tangent line will underestimate. Second derivative positive means the function is concave up. If we have a concave up curve and we put a tangent line to a concave up curve, it's going to go under the curve and be an underestimate. All right, so problem 2 is going to direct you to create the tangent line at x equals 8 for the cube root of x, and then estimate the cube root of 8.2 using the tangent line. Question 3 is going to ask you to do something similar, but with the tangent line at pi over 4 to estimate what the tangent of pi over 4 plus 0.02 would be. And then problem number 4 really boils it down to bare bones. Gives you 3 pieces of information. It gives you a point, it gives you a derivative value, a first derivative value, and a second derivative value. You're supposed to create the tangent line at 2. To then estimate the function value 2.01. And then from the second derivative information, you should be able to tell if it's an under or over estimate. You should go ahead and try those 3 problems, and in the second video I will go through all 3 of them.